So now we'll solve this problem where what is involved is to take something like this, where we have a force field, and use it in Newton's equations of motion. So this is just like the spring force, the restoring force. So we have a mass, M, moves through a force field defined by F, and here X is the position of the particle. So in this question it should say that lambda is strictly positive. So we're asked to determine the position of the particle as a function of time, and then find the potential energy of the particle, and then determine how its speed depends on the position of the particle. Okay, so for the first part we need Newton's equation of motion. This is m dv by dt equals f of x in this case, because that's our force field, that's our right hand side. We now know that this gives us the following. And due to the fact v equals dx by dt, velocity is rate of change of displacement, we have m d squared x by dt squared equals minus lambda times x. Now, should know how to solve these. How to solve quickly. Okay, so you can see this, what I'm about to do, from this module, because you did this many times at the start of the semester. So effectively, we need to solve an equation of the form it's like this: d squared f by dx squared equals minus lambda, I'll put lambda, times f. Lambda isn't the same lambda as in this is just an aside problem. It's not the same lambda as in the question. Okay. And if what you should verify for yourself, is I would do this, is if lambda is greater than 0, then the solution looks like this. Okay, I think we tackled this before. In other problems. Important case, and this is a challenge. Okay, sorry. Important case is this. Here's the challenge coming up. So this is something for you to work at. And once you've showed these formulas, proven them to yourself, you should remember them. Because these are simple differential equations, you should try to understand how to solve. Okay, so we're going to do something different now. Okay, so now if we have this equation, here's the challenge. You should do this alone. Now show that the equation. So the first equation, the first solution I showed you can do with the methods from MAT 10046. Now, once you've done that, maybe you can try and show this. So if I have this equation now with lambda here being positive, then the solution is this. where the solution uses hyperbolic functions instead of trigonometric functions. Okay, so this is an aside. So back to the problem. So we got this m d squared by dt squared of x, how did I write it, equals this. Lambda and m are greater than 0. If I divide through by m, then I have this. And clearly this is greater than 0. So using what I've just showed above, I can write x of t equal to a sine the square root of lambda over m x times b cos square root lambda over m, all multiplied by x. Okay, so this is my displacement. So that answers the first part. Determine the position of the particle. Position as a function of time. Okay, next part. Let's see. Find an expression for the potential energy of the particle. Well, that's easy. Why? Because we actually know this thing here. So we know that f of x is equal to minus lambda x. We know that the potential energy for the system, so this is part 2, potential energy is this. It is v of x equals the integral, or minus the integral, of f of x dx. So if I just substitute this in, well, this gives me this. Just by direct substitution, I can bring the minus and the lambda outside. So this gives me lambda times the integral of x with respect to x. So that's integral of the displacement with respect to the displacement. This is really easy to calculate. So v of x. Don't forget, here we don't need to add the constant because that goes into our energy, total energy for the problem. So v of x is, when we do the energy balance, the constant will go into the total energy. So here we just omit the constant, so that v of x is this. Okay, and that's it. So then we would have a kinetic energy law. Don't forget that this goes straight into V plus T equals E. So this is what we found. We know that this here is 1/2 m v square, where v is dx by dt. Okay, and this here was the constant of integration that I told us to omit, because all of this is going into, when we're doing this process to derive this equation, the constant goes into this constant of integration, and it's the total energy. So, with this in mind, we're well set up for part 3. Part 3 now is really nice, easy to do, because what we have is 1/2 from this, from star, we've got 1/2 mv squared. Now remember, this is v of t. Okay. And this, now we know what our potential energy is. So this is V, capital V of x. And this should equal E. Okay. Now, let's just check if we have any conditions. No. Okay. So, how does the position depend on, the speed depend on the position of the particle? Well, here to find speed, we should rearrange. Remember that speed is the magnitude of the velocity, so rearrange for modulus of v. So I'm going to take this equation. Okay, I'm going to take this equation and just begin to okay, so now what you'll notice is I can multiply both sides by 2, so that I get mv squared plus lambda x squared equals E times 2. Then I have v squared equals 2e minus lambda x squared over m. And note that v squared is modulus of v squared, and this is speed. So, modulus of v, the speed, is the square root, positive square root of 2e minus lambda x squared over m. All right. Now, here I have to make a point that 2e should be greater than lambda x squared. Otherwise, what happens is, so this means x squared, or the modulus of x, should be between the square root. Oh, sorry, modulus of x should be less than this. Because if modulus of x is greater than this value, this makes no sense. Also note also, if I take a look at this, speed is maximum. Oh, sorry, speed is 0, not maximum. Speed is 0 when, by the way, that should be less than or equal to, this should be greater than or strictly greater than. So the speed is 0 when x takes a value at the extremities of the interval. This interval minus square root of 2e divided by lambda, square root 2e divided by lambda, i.e. when x equals plus or minus the square root of this. And this is the max distance, the maximum distance. Corresponds to the maximum distance the particle can travel under this force field. To the max distance particle can travel under this force field. Okay, so that's a very important point about the energy balance. It's just revealed this information. If an object moves under such a force field, then the motion of the object's bounded, and its velocity is instantaneously, or speed is instantaneously zero, or velocity even, when x is at the extremities of this interval. And this corresponds to an oscillating motion. So also corresponds to the oscillating motion of a mass on the end of a spring. So in the theoretical model, for a mass connected to a spring, the mass moves to the left and the right between two values. And of course, in reality, this doesn't happen because you have things like physical things like internal dissipation in for instance, the spring, and then of course the mass will want to settle to rest. Okay, so in this case, this theoretical model predicts that we have the mass moving between 2 points, and when you reach the ends of the interval, the speed of the mass is zero. Okay, so that's all for this example. So see you next time for an example where we'll look at a nonlinear force field.